Dear ladies and gentlemen, let me present the findings of joint research, Technology of Ukrainian-English Machine Translation based on Recursive Neural Network as Long Short-Term Memory. The research was developed by Myroslav Konyk, Victoria Vysotska, Svitlana Holoshchuk, Roman Holoshchuk, Sofia Chyrun, and Ihor Budz. To begin with, I should say that neural machine translation is a recently proposed approach to machine translation that differs from traditional statistical machine translation as it focuses on building a single artificial neural network that can be jointly configured to maximize translation performance. In recent years, the technology of neural machine translation based on artificial neural networks with representation learning has rapidly developed. That's why the purpose of our study is to create an intelligent system of Ukrainian-English translation using the means of neural machine translation. To reach our purpose, we have set the following objectives: to study and compare related works and applications, to conduct a system analysis of the developed product, to develop unified modeling language diagrams such as use case diagram, components diagram, and activity diagram, to identify methods and means of the developed product, to present the general architecture of the sequence-to-sequence model using long short-term memory layers, to perform system testing to evaluate system specifications and describe the results, to make the training statistics of the model with a description of its outcome. Now we would like to outline the advantages of using neural machine translation. Unlike other approaches, such as statistical machine translation and rule-based machine translation, neural machine translation uses an extensive neural network that applies artificial intelligence to work like the human brain. Advantages of using neural machine translation include high accuracy, fast training, simple integration and flexibility, customization, cost efficiency, and scalability. Related works and applications are the following. The first one is Google Translate. So Google Neural Machine Translation is a neural machine translation system developed by Google that uses an artificial neural network to increase fluency and accuracy in Google Translate. Google Neural Machine Translation improves the quality of translation by applying an example-based machine translation method in which the system learns from millions of examples. The next one is Microsoft Translator. It is the main competitor of Google Translate. It is a cloud service from Microsoft that offers machine translation in various languages. It is available for multiple platforms and can be easily used by anyone. Another application is open source neural machine translation. It is an open source ecosystem for neural machine translation and neural sequence learning. The advantages of neural machine translation systems are that they are end-to-end models that do not have a pipeline of specific tasks. The disadvantage is the need for a bilingual set and the ongoing problem of processing rare words. Materials and methods we used are the following. The Python programming language and the Jupyter programming environment are used to develop the neural machine translation system. A set of Keras tools is employed for the neural process of building the model. The general architecture of our model is presented here. It is a sequence-to-sequence neural network model with inner layers of recurrent neural networks. Each sequence-to-sequence model contains two main components. Encoder outputs some value for each word in the input sentence. For every input word, the encoder outputs a vector and a hidden state and uses the hidden state for the next input word. Encoder reads the input sequence and summarizes the information in the internal state vectors or context vectors. In the case of long short-term memory, these are called the hidden state and cell state vectors. We discard the outputs of the encoder and only preserve the internal states. This context vector aims to encapsulate the information for all input elements to help the decoder make accurate predictions. And the second one is decoder. It reads the encoder's output vectors and outputs a sequence of words to create a translation. The context vector of the encoder's last cell is input to the first cell of the decoder network. Using these initial states, the decoder starts generating the output sequence, and these outputs are also considered for future work. On this slide, you can find the visualization of the architecture of our neural machine translation model. Long short-term memory is a type of recursive neural network capable of learning long-term dependencies. The architecture of our sequence-to-sequence model is defined as: we will use an embedding layer and a long-term short-term memory layer for the encoder. We will use another long short-term memory layer for the decoder, followed by a dense layer. Use case diagram describes the set of actions that a specific system or system must or may perform together with one or more external users of the system's actors. This diagram is the initial conceptual model of the system in the process of its design and development. It consists of actors, use cases, and relationships between them. A different diagram is a component diagram. It is a unified modeling language element having a static diagram structure. It shows structural components of the software system and the relationships between them. One more diagram is activity diagram, which is another crucial behavioral diagram in unified modeling language diagram to describe dynamic aspects of the system. An activity diagram is an advanced flow chart that models the flow from one activity to another in the system. The first thing we need to do is to input the necessary libraries. Next, we will write a function for reading data in Jupyter Notebook. Then another function for dividing the text into English-Ukrainian pairs separated by a symbol /n is defined. Further, we correspondingly split these pairs into English and Ukrainian sentences. Now we can use these functions to read text into an array of the necessary format. The actual data consists of over 150,000 sentences per. However, we will only use the first 50,000 per item to reduce the training time of the model. Now, let's have a look at the results. So, we pre-process the text. It is an essential step in any project, especially in NLT. The data we process is often unstructured, so there are certain things we need to take care of before moving on to the model building stage. The first stage is text cleaning. We analyze our data as it helps us decide which pre-processing steps to take. The next step is to remove punctuation and convert text into lowercase. Further, we convert text into a sequence. The sequence-to-sequence model requires us to convert input and output sentences into fixed-length integer sequences. Before doing that, we visualize the length of the sentences by collecting the length of all sentences into separate lists for English and Ukrainian languages. The obtained sequences of integers representing predictions are converted into an English text. And you can see the part of this process on the slide. Finally, we can run a benchmark test and review the results. Next, we place the original English sentences in the test dataset and the predicted sentences in the data frame. Finally, we can run a benchmark test and review the results. Here we present the obtained results of the last 15 pairs. Now we would like to describe the model training statistics. For this, we apply a function called model checkpoint. Model checkpoint callback is used in conjunction with training using model.feed to save a model of weights in a checkpoint file at some interval, so the model of weights can be loaded later to continue the training from the state saved. As we can see in the diagram above, the validation loss ceased decreasing after 25 epochs. So let's move to conclusions. The paper presents a novel approach to developing Ukrainian-English machine translation technology using neural machine translation. A comparative analysis of the developed software product with analogues such as Google Neural Machine Translation, Microsoft Translator, and OpenNMT was conducted. System analysis of the developed product was carried out, and unified modeling language diagrams were constructed, such as use case diagram, components diagram, and activity diagram. We proved the advantages of Python, the Keras toolkit, and the Jupyter Notebook development environment as the necessary tools for our work. The general architecture of the sequence-to-sequence model using long short-term memory layers was also presented. Having analyzed the software process and its structure, we performed system testing to evaluate system specifications and described the results. The neural network model test results have shown that the confirmation loss stopped decreasing after 25 epochs. All things considered, it seems reasonable to assume that future research should explore improving the translation system accuracy and increasing the model speed, which will involve exploring additional or alternative architectural solutions. That's everything I wanted to present to you. Thank you very much for your attention.